Hello everyone. So today I discuss the sort of applications of nuclear chemistry in determination of analytes in different types of matrices using a technique called nuclear analytical techniques. Nuclear analytical techniques are those techniques which are based on a nuclear phenomenon, like for example, nuclear reaction. So when we have a tool in the form of a neutron, you have a charged particle beam, depending upon whether you have a neutron as a projectile and you want to do some analytical chemistry using neutrons, then we will call it neutron activation analysis. That means you activate a sample with neutrons, and the radioactive radiations emitted by these activated products you are monitoring, and that tells you about the concentration of the elements in the sample. So that technique is called neutron activation analysis. And in today's lecture, I will deal with neutron activation analysis. In the first part, I will tell you about the principles, the fundamentals of this technique. And in the second part, I will be talking about some of the applications of this technique, just to bring home the point how important these techniques can be solving many problems. And the second part I will take next time, that is the ion beam analysis, where we use an accelerator providing the charged particle beams of protons, alpha particles, or even other ions, heavy ions. And so these charged particle beams can induce reactions, or they can be just simply scattered at a forward angle or backward angle. And based on these interactions, again, we can characterize a sample for its constituent elements, or you can even understand processes involving these elements. So both these techniques are clubbed as nuclear analytical techniques. And in fact, you will see later on how kind of information that we obtain about these techniques, some of them are not possible by other techniques. So I will discuss both of them one by one. So the first technique, as I was mentioning, is the neutron activation analysis. As the name itself implies, that if you want to characterize a sample for its constituent elements, then we can activate the stable isotopes of the sample by neutrons. And as you know already, by that neutron is captured by the different isotopes, and you can get radioactive isotopes. In some cases, even if you don't get radioactive isotopes, you can determine the prompt gamma ray to characterize the constituent elements. This technique was developed by George Hevesy, a scientist who in fact also gave the tracer concept, which I discussed in the last lecture. George Hevesy, along with Hilde Levy, developed this technique in 1936, and since then it has become so popular among analytical chemists. Not only analytical chemistry, but there are many fields in which this technique is being utilized. The best part of this technique is that, of course, at the same time, you could just irradiate one sample, you can determine simultaneously several elements in the sample. Whichever elements are amenable to neutron activation analysis, you bombard them, and you get radioactive isotopes. Sometimes even if you can get prompt gamma rays, so then you can determine the concentration of these elements. And a diverse matrices can be studied by neutron activation analysis. It is highly sensitive because the signal that you get in terms of the gamma rays, you get high yield, particularly nowadays if you have a availability of high flux nuclear reactors. So the reactors these days give neutrons of the order of 10 power 13, 10 power 14 neutrons per second, centimeter square per second. And because of that, you can assay even the nanogram, in some cases even picogram quantities of the isotopes. And secondly, this availability of high flux nuclear reactors coupled with the high efficiency, high purity germanium detectors. So you require high efficiency. I will discuss in details what are the factors that govern the sensitivity of this technique. In the periodic table, if you see, as many as 70% of the elements in the periodic table are amenable to neutron activation analysis, like for example, sodium, potassium, magnesium, calcium, vanadium, aluminum, and so on. So there is an endless list, almost, rare earths, odd earths, many of the actinides, they are amenable to neutron activation analysis. You see, it is not necessary that every study has to be done using neutron activation analysis, but it has got an edge over other techniques in many cases. In those cases, you find this is very, very useful. So, neutron activation, first of all, it is not destructive because you can preserve the sample for subsequent analysis. And that is why it finds particularly the useful, the like archaeological samples, geological samples, which you don't want to destroy, you don't want to dissolve and then analyze. So you want to preserve them for any further artifacts. So such cases, neutron activation analysis finds a lot of applications. So you can have biological samples, geological samples, environmental samples, forensic analysis samples, archaeology, even medicine, and of course in nuclear technology. So there are a lot of fields in which the determination of elements are required. For it can be forensic application, it can be just chemical quality control of the materials, and even other areas like archaeology, geology. So neutron activation analysis, if you see in analytical chemistry and other fields, you will find it is very popular technique. Only thing is you require to have a source of neutrons. Okay, so let me just discuss what is the fundamental principle of neutron activation analysis. When a isotope captures a neutron, I have written the mass number A, capital X is the element. So when it captures a neutron, the isotope of the same element is formed, A plus 1X. And what I have shown is the sort of potential well of the target, the compound nucleus that is formed. So the reaction involves capture of neutron by AX to give you A plus 1X. And in this capture reaction, energy equivalent to the binding energy of neutron in this nucleus is released. Like when a neutron is captured by a nucleus AX, certain energy is released. That Q value is positive for all neutron capture reactions. And so that energy that is released, the Q value is equivalent to the binding energy of neutron in that nucleus. So this nucleus is excited. For example, if you have a nucleus 59 cobalt and gamma 60 cobalt, this cobalt 60 nucleus is excited, let us say 60 cobalt, excited state, and this is the ground state. So this excited cobalt 60 nucleus having excitation energy of about 7 MeV, first will emit the gamma rays. So these gamma rays that are shown here, they are called the prompt gamma rays, because the excited state will de-excite its gamma ray within picoseconds. So very quickly within picoseconds, yes, either one or several gamma rays may be emitted. These prompt gamma rays themselves can be counted online by a HPGE detector. So you can determine the concentration of this isotope using the measurement of prompt gamma rays emitted by the sample. And this technique is called prompt gamma neutron activation analysis. Now, since these gamma rays are emitted instantaneously upon capture of a neutron, this is essentially an online measurement. Means while the neutrons are radiating the sample in the reactor, you have to do the measurement. So how can you do that? So for that, neutron beams are taken out of the reactor, and you have an arrangement where the neutrons are available to you in the outside the beam reactor hall, and where you can put your sample and the detector system, and then you can do the measurement of gamma rays. In such a situation, in PGNAA, so suppose you irradiate, your irradiation is going on, you count the sample for, let us say, some time, say half an hour. So that counts that you will get in that half an hour is number of target atoms in the sample, because all atoms are being exposed, the cross section for the neutron capture, the flux of the neutrons in that position, the time of irradiation, efficiency of detection of the gamma ray, and the intensity of that gamma ray. So you can see here, if you know, if you irradiate, if you do experiment for certain time t, and whatever counts you get, you can find out the number of atoms of the target element and hence the concentration of it. Because cross section is the capture cross section, which you know. Flux, you have to do some experiment, you use some monitors. There are some flux monitors, some standard samples where concentration is known. You can find out the flux. Detection efficiency, you should know using standards, you can find out. And the intensity of the gamma ray, for say for how many times this gamma ray is emitted if that atom is formed. So all these are nuclear data which are available in the literature. So this is the prompt gamma neutron acquisition analysis. You need to do the experiment in the online, either in a reactor, or if you have a neutron source like a californium source, or you can generate neutrons in an accelerator site by spallation neutron sources. So you can do that way. But if you measure the gamma rays that are after beta minus decay, then these gamma rays are actually called offline gamma rays or beta delayed gamma rays. In that case, for example, cobalt 60 having half-life of 5.27 years, you irradiate for some time, take out the sample of the reactor, take it to the laboratory, and the half-life of cobalt 60 is 5.27 years. So you can comfortably do the measurement in the laboratory. So these are measurement of delayed gamma rays, and this is the offline gamma ray. The bulk of the neutron acquisition analysis is usually done using delayed gamma measurements. This is called NAA, neutron acquisition analysis. Now you are actually measuring the concentration of a radioactive sample. So you are counting the radioactivity, and what you get is the counts per second. You take a gamma spectrum for a particular length of time and divide the peak area by the time, you call counts per second. That count per second is a familiar equation, and sigma phi is the rate of the reaction, neutron capture, the saturation time for particular irradiation time, the decay after the end of irradiation, radioactive sample is decaying with its own half-life, efficiency of detection, and the intensity of gamma ray. So this you can get the number of target atoms in the sample. So how do you get the concentration? This is the mass of the element of interest. Number of atoms of target element is mass of the target element of interest. Now it can be a multi-isotopic sample, like for example, cobalt is monoisotopic, so this is only one isotope, but you have tin, you have many isotopes, iron, you have many isotopes. So abundance of that particular isotope is theta, Avogadro number, and the atomic mass. So if it is a multi-element, multi-isotopic sample, then average atomic mass will be different from the mass number, And so what you can determine is the concentration, M. M is the parameter of interest to you. Now, quickly, I will just give you that the theta is the isotopic abundance. So you can see these are the monoisotopic elements where only one isotope is present in the sample. So 100% abundance of arsenic 75, manganese 55, scandium 46, sodium 22, and the remaining ones are, you will find the even ones, even Z elements. So they have more than one stable isotope. Aluminum is monoisotopic. So the abundance of the isotopes will vary. These are the cross sections for the particular isotope neutron capture reaction. And so they are in bond, and these are the products that are formed after neutron capture. They are formed, they are their half-lives, the gamma ray, and then the intensity of the gamma. So you can see here, gamma ray intensity, some of them have 100%, means every decay, it could be beta minus or electron capture, will give you one gamma ray. So abundance is 100%. Gamma ray abundance or gamma ray intensity is 100%. So you can see here, the sensitivity of the detection of the elements depends upon the isotopic abundance, the capture cross section, and the intensity of gamma. So essentially, under the gamma ray peak, you get a peak area. That peak area will be more if the isotopic abundance is more, if the cross section for neutron factor is more, and if the intensity of the gamma ray is more. Other parameter is flux, so that doesn't depend upon nuclear data of the isotope, but another quantity is the neutron flux in the reactor. So these parameters you need to maximize to get high sensitivity. Even these are the for other isotopes. So there are several isotopes, as I mentioned, are amenable to neutron activation analysis. You can see some of them. You see the monoisotopic ones. So they will have more sensitivity because there is only one isotope present in the stable isotope. Okay, so let us discuss the sensitivity and detection limit of neutron activation analysis. As I mentioned, the count rate in the neutron, when you irradiate a sample with neutrons. Now we are discussing about neutron activation analysis. That means you do an offline, you do irradiation, take the sample out of the reactor or neutron source and count the activity of the radioisotope in the laboratory. So that is the offline measurement. So again, this is the same equation which I mentioned in the previous slide. This essentially gives you the number of target elements. This is the cross section and the flux, the saturation time, the cooling time, the decay time, efficiency, and abundance of the gamma ray, intensity of the gamma ray. So what is sensitivity? Suppose you irradiate 1 microgram of the sample, how many counts per second you get? That is called the sensitivity. So counts per second per unit mass, let us say per microgram. So sensitivity can be written as CPS per microgram or CPS per milligram or CPS per nanogram. So if you have a sample containing 1 microgram or 1 nanogram or 1 milligram sample, what is the counts in your detector? Suppose this is the gamma spectrum. So this peak area, you can put the limits, and so this is the peak area of the gamma ray peak, and this is the background. Below this is the background. So you have to subtract the background from the gross count. So when you put the two limits, area under this graph will be gross counts, and then you do a linear subtraction of this background. So if this trapezium you subtract, you get the net peak area. So this peak area will be high if flux is high, cross section is high, efficiency is high, gamma ray intensity is high, isotopic abundance is high. So that determines the sensitivity of the technique. Second quantity is the detection limit. How much is the minimum quantity that you can determine by this technique is called the detection limit. Now, how do you define the detection limit? So normally now when you will, suppose there is no sample, if you take a gamma spectrum, you will get a flat background counts, or there could be some bump here. So that bump, small bump, it may be confused as the sample, the gamma ray spectrum due to the sample. So we do not know how much is the amount that will give you a reasonable peak area. So what is essentially done is, it's called the Curie's law. That means if you take a background of a sample, suppose you have a blank, that sample doesn't, you don't have a sample, you just record the gamma ray spectrum. Then in the position of this gamma ray peak, you will get, and you define these limits, upper limit and lower limit of the peak, you will get some background counts. And you suppose you take multiple times the background. That's if you, and then over now next time you count the sample. So suppose you get some higher counts. How will you make sure that there is that detectable amount of that particular element? So the thumb rule for that is the level of detection is the 3 sigma background. Now 3 sigma what is the background of the background count? Standard deviation, sigma b means standard deviation of the background count. So suppose you have b counts in the background, sigma b is, this is the square root of the counts, is the standard deviation, because variance is equal to mean or the detection. When you are doing gamma ray, any counting, you do radiation counting, they follow the Poisson's distribution. And so Poisson's distribution, variance is equal to mean. That means sigma square equal to mean. And so the standard deviation is equal to square root of the mean value. Now, how do you want to quantify that? If it is this much time of standard deviation, we say there is a confidence limit, this much probability that their sample contains some element of analysis. So 3 sigma essentially is a, suppose you have a Gaussian distribution of the background counts. So this is the mean background counts, and this is the 1 sigma B. You have 2 sigma and you have 3 sigma. So these are corresponding to different confidence level. This is called the 68% plus minus 1 sigma, 95% and 99%. So 99% of the time, that means your sample contains that particular element. So now if it is limit is 3 sigma, means it has to be more than background plus 3 sigma. So 3 sigma is essentially an indication of a confidence limit of 99%. You are 99% sure that your sample contains that element. That is the limit of detection. 3 times the square root of the background counts under the peak. So you can see here, or the detection limits for different elements are given here in terms of picograms, DL values. Like dysprosium and europium have a detection limit of 1 picogram. That means if you have a picogram of a sample of these elements in a sample, by neutron activation, you will get a measurable. So over the background, you will see a bump that you can quantify. So this is called the, you can actually detect that yes, it contains that element. There is something called limit of quantification that is more than 3 sigma. It is actually 6 times the sigma. Then you want to quantify how much the concentration. Here you want to test it, you can detect it. 1 to 10 picogram, indium, lutetium, manganese. So this essentially tells you the decay characteristics, the nuclear data, the cross section for neutron capture, the gamma ray intensity, isotopic abundance, and so on. 10 to 100 gold, holmium, 100 to 1000, 1000 to 10,000, 10,000 to 1 lakh, 1 lakh to 1 million, and 10 million. So different elements have different sensitivity of detection in the neutron activation analysis. So you can choose. It is not necessary that you have to follow the neutron activation technique to determine concentration. These days you will find there are very sensitive techniques like inductively coupled plasma atomic mass spectrometry, inductively coupled plasma atomic emission spectroscopy. You can have a source, you can excite, you can generate a plasma, and the excited atoms decay, and then you can measure the gamma ray, the visible photons emitted by these atoms, or you can generate plasma and then see emission lines of this one, or you can do the mass spectrometry. So depending upon the what you measure, you can have ICP-AES or ICP-MS, and these ICP-MS techniques can go up to picogram per gram, parts per billion. So there are techniques now, but then what you need to do, you need to dissolve the sample and you need to do the analysis. But in this particular case, you just take the solid sample, you radiate in the reactor, and you can get the gamma ray. So the sample is intact. You can again repeat the experiment, or you can preserve it for future analysis. So that is the beauty of this neutron activation analysis. Okay, let us discuss the how do we determine the concentration. So there are mainly 3 methodologies I will be discussing. First is the absolute method of NAA, neutron activation analysis. Absolute method means you use this equation, counts per second. This is the concentrate the amount of the isotope of element interest, isotopic abundance. So this is the NT, sigma phi, saturation factor, and the decay factor, efficiency and detection, and the intensity of the I gamma. So you want to determine M in the absolute method. So you need to know cross section. You anyway know in the reactor what is the flux at that position, This factor can be determined easily. Efficiency, detection efficiency, gamma ray intensity is known. These are also are known. So what you can find out the M from this expression, provided you know sigma and phi. So sigma and phi, sometimes you may not know exactly, like the flux. The reactor is a big place where the flux at a particular position may not be accurately known because the flux is not constant all along the reactor. So this absolute method requires that you should have the data on cross section and phi. So generally, this is not a preferred method, but sometimes you may not have any choice, so you have to go for absolute method. The most common method is comparative method or relative method. That means if you have a sample where the concentration of that particular element is known, that's called the standard. And with respect to that, you can determine the concentration in the sample of your test. So what you do in this, you irradiate the sample and the standard together. So the irradiation time is same. You are determining the gamma ray of the same isotope. So the saturation factor is same. Detection of efficiency, gamma ray intensity, cross section, flux, all are same. What is different is the M. So if you see CPS sample will be proportional to, now this all will get cancelled. What you have, MS e raised to this D factor you are counting at different times, DS upon and it will be, so M standard, D standard, okay, so this is upon CPS standard. So you can count rate of the sample, count rate of the standard, mass of the element in the sample, mass of element in standard, decay factor for the sample, decay factor for the standard. So what you get is the M, this value, mass of the element in the sample, mass of element in standard, which is known, count rate in the sample upon count rate in the standard, the decay factor, this factor. So these are all very simple quantities. There are standard reference materials for which the concentrations are known. There have been inter-laboratory comparison experiments done worldwide to establish the concentration of the analytes in samples, and those standards can be not even purchased from the source. Then there are certified reference materials, and there are working standards. You can prepare a standard in your laboratory. Suppose you take a compound of known stoichiometry, which is not hygroscopic, you can use for the particular element that standard. Working standards, CRMs, certified reference material, and standard reference materials, either of them you can use. So this is the most commonly used method. But then there are situations when you do not know. Suppose you have a new sample which you don't know what are these elements in that. So how can you have a reference for that? Unless you know the elements, you don't know how to make the standard. So that this new development has taken place called single comparator, K0NAA, K0NAA, neutron activation analysis. That means this is in the absolute method, for every element you have to have a standard amount in the sample. So you require concentration of the element to be known in the standards. So suppose you have 10 elements, all the standards would have all those 10 elements. But if you have single comparator method, then you determine the concentration of all the elements with respect to the single comparator. Like gold you can use as a single comparator, or manganese or scandium. So you irradiate a gold standard with the sample, and you determine the gamma ray activity of gold and the sample. And there are no methodologies by which you can find out the concentration of the element with respect to gold. Gold is already known, so you can determine the concentration. So this single comparator becomes very popular for unknown samples where you do not know what are the elements present in that particular sample. I am not going to give details of this K0NAA. This is a bit more elaborate methodology where you require to know the flux in the reactor. You need to calibrate the reactor position for the flux, past flux to thermal flux, So because the cross section for the gold is now, as I was telling, now the cross section follows 1 by V law. There are some resonances at higher energy. So the flux of the neutron, or as a function of energy of neutron, the cross section of the element, the isotope as a function of neutron energy are required to be known. So it is a little bit more elaborate experiment. So lastly, what are the advantages of neutron activation analysis? One, it is the simultaneous multi-element determination. In the same time, if you irradiate a sample, whatever elements in that sample are amenable to NAA, determined by this technique. It is generally non-destructive. Suppose there can be cases that you can introduce a lot of activity and you may not be able to handle it, but after some time anyway the activity will die down, and so you can reuse the sample. So it is in general, you can say, non-destructive sample. You can preserve the sample, and after the radioactivity dies down, you can use it. Matrix effects are largely negligible. Suppose this is like interference. There are very few isolated cases where the two elements will give the same gamma ray. Even if they give the same gamma ray, there may be different half-lives, so you can resolve them. So that way, matrix effects are negligible, unless you have a very high, an element which has got very high neutron absorption cross section, the flux may get reduced. Highly selective, because the radioisotopes that are formed, they have distinct gamma ray. So it is distinct, even if the gamma ray is same, you have different half-lives. Highly selective, high sensitivity because of the high cross section, high flux, high detection efficiency, you have very high sensitivity, and so high precision and accuracy. They are quite reproducible, and the data can be obtained very. So because of these advantages, neutron activation analysis is called a reference techniques. That means for many like forensic applications or many applications, data provided by neutron activation analysis are taken as reference data. So they are even in the, suppose you have forensic data in a court also, this data can be used to as an evidence for the data. So these are the advantages, and neutron activation is well studied, very common technique, not only the analytical chemistry, but many other areas which I will discuss in the next lecture. The neutron activation is used. So I'll stop here. Thank you very much.